All right, so what we're doing now is we're working on problems that have to deal with thermochemistry. So this entire unit, or these problems that we're going to be discussing, are going to have to deal with thermochemistry, all right? So the first question states, consider the following balanced equations. So we have magnesium carbonate decomposing into magnesium oxide and carbon dioxide. Decompose, remember that word, I'll explain that in a few minutes, how to think about it in terms of energy. Following thermochemical equation for the decomposition of a mineral magnesite. All right. The first part of this, A. First part A. The question asks, is heat absorbed or released in the reaction? Now, the key word there is decompose. If something's decomposed, it means heat's got to be added to it. So simply from that word, we know that heat is going to be added to the system. We also can look at the enthalpy term and see that it is positive. If we have a positive enthalpy, that means that heat is absorbed by the system. All right, so that's going to be our system. B, what is the delta H for the reverse reaction? So if we're going to write this in reverse such that the products become the reactants, then our delta H is going to be negative. So B, it's going to be, the delta H for the reverse of what we have here is equal to a negative 117.3 kilojoules per mole. C asks, what is delta H when, so we have 5.35 moles of CO2 reacts with excess magnesium oxide. So we're writing the reverse of this. So this becomes moles of CO2. And now, if we have the reverse of this, right? If we're asking carbon dioxide to react with the magnesium oxide, then for every 1 mole of CO2, it's going to release a negative 117.3 kilojoules of energy. If we do that arithmetic, what we end up getting is we get 627.56 kilojoules. Now for D, D asks, what is delta H when 35.5 grams of CO2 reacts with excess magnesium oxide? So basically it's the exact same question we had in C, except we have to convert it into moles. And for every 1 mole of CO2, that's going to be 32 for 2 oxygens plus 12 is 44 grams of CO2. Now, 117.3 kilojoules per mole of CO2. All right, and that's going to give us 94.64, I'll just stay consistent, kilojoules. Now, the one thing I forgot to mention, and I apologize for that, is that our units cancel in the following step. And we're left, in this case, in units of kilojoules. Here we're left in units of kilojoules. Okay? It's going to deal with calorimetry, all right? So what we have is we have a 30.5 gram sample of an alloy with an initial temperature of 93 degrees Celsius is going to be placed into 50 grams of water, and the initial temperature of that water is going to be 22 degrees Celsius. Upon putting the alloy into the water, the temperature is going to rise to 31.1 degrees Celsius for both the alloy and the water, because it's going to come to thermal equilibrium. The heat capacitance of the calorimeter is 9.2 joules per gram degree Kelvin. Now, we're going to leave this in Celsius. And the reason being is we're going to have a change in temperature. A change in temperature in degrees Celsius is the exact same number as a change in temperature in Kelvin. All right? Now, the key equation we need for this is that the alloy loses heat to the water. because we know that that happens because the temperature of the alloy is higher than the initial temperature of the alloy is higher than the initial temperature of the water. So when the alloy goes into the cold water, it's going to give up its heat. Remember that Q is equal to mc delta T. So let's just start working with the alloy. So we're going to leave our negative there. The mass of the alloy is 30.5 grams. We're looking for the specific heat. The change in temperature is going to be the final temperature minus the initial temperature, and that's going to deal with the alloy. So now we're done with this part, is equal to mass of the water, which is going to be 50 grams times the calorimeter constant for our calorimeter, which is 9.2 joules gram Kelvin. Remember, the change in, I'll get to that in a few seconds, sorry. Now, if we look at the final temperature, it's going to be 31.1 minus the initial temperature, which is 22. So now, remember, numerically, we left this in degrees Celsius, but the change, the difference in the temperature, is going to be the same whether it's Kelvin or not. So our grams cancel with our grams. We're going to leave the grams there because that's going to go into that. The Kelvin here is going to cancel with the Kelvin there. All right. So we go through and we do a bunch of arithmetic, right? So we're going to get a number here. We're going to get this. So we can multiply those two numbers. And what we end up getting here is we have a negative value here. We have a negative here, so this becomes positive. So when you take 30.5 times the difference in that, what you get is 1,887.95 C, which is ultimately what we're looking for, is equal to, if you take the difference here, so this is going to be what, around 9.1, right? 9.1 times 9.2 times 50. What you get is you get 4,186, and the units here are going to be joules, right? So now you divide both sides by 1887.95, and you get the heat capacity, which is equal to 2.22 joules gram Kelvin, because the units here are going to be gram Kelvin. And so the heat capacity of our alloy is 2.22 joules grams Kelvin. Okay, 1. All right, for the next question, what we have is we have a 295 gram aluminum engine part that has an initial temperature of 13 degrees Celsius, and added to that is going to be 75 kilojoules of energy, which is equivalent to 75,000 joules, and the specific heat of that engine component is going to be 0.900 joule gram Kelvin, right? Joule gram Kelvin. Now, the equation we're going to want to use for this is Q equals mc delta T. Q equals mc delta T. Now, we're going to solve for our change in temperature because we're looking for a final temperature. So delta T is going to be equal to Q upon mc. Our Q is going to be 75,000 joules. Our mass is 295 grams. Our specific heat is 0.900 joule gram Kelvin. Now, if we look at the units, if we watch what's going to happen to these units, the grams cancel, joules cancel, joules cancel. And what we have is 1 over an inverse, such that the units of this are going to be in kelvins. It's going to be in kelvins. So if we do this arithmetic real quick, we'll find out that delta T is 282.5 Kelvin. That's our change in temperature. Since heat is added to this, we know that the final temperature is going to be greater than the initial temperature, and so T final is going to be equal to T initial plus delta T, and this is going to be equal to 13 degrees Celsius plus 282.5 Kelvin, degrees Celsius, because a change in temperature Kelvin is equal to a change in temperature Celsius, and so this becomes equal to 295.5 degrees Celsius. All right. Once again, a change in temperature at Kelvin is the same numerically as a change in temperature in degrees Celsius, because you're just simply adding 273.15 to it. All right. All right. We have yet another problem that has to deal with calorimetry. So the problem states an unknown volume of water initially at a temperature of 18.2 degrees Celsius is placed or is added to a volume of 24.4 milliliters of water that is at 35 degrees Celsius. When that is accomplished, the final temperature of everything is going to be 23.5 degrees Celsius. So the equation we have is we have minus Q of the hot is equal to Q of the cold. Now, when I mean hot and cold, what I mean is initial, all right? So this, the unknown is the cold because it's at a lower temperature than the hot. The initial temperature, this is 35 degrees Celsius, so this is going to be the hot. And as we look at this equation, if we write this out, this can be minus M of the hot, specific heat of the hot, delta T of the hot is equal to the mass of the cold water times the specific heat of the cold water times the change in temperature of the cold water. Now, because both the unknown and known are water, we know that CH is equal to CC, so therefore we can cancel those out. And so the equation we have here is minus mH of the hot times delta T of the hot is equal to the mass of the cold times the change in temperature of the cold. Now, if we look at the mass of the hot, they gave us 24.4 milliliters. We know that the density of water is going to be 1 gram per milliliter. It's going to be 1 gram per milliliter. And so we know that 24.4 milliliters of water is going to be equivalent to 24.4 grams. So this becomes minus 24.4 grams times temperature of the hot, so the change in temperature, which is going to be the final 23.5 minus the initial, which is 35 degrees Celsius if we're worried about our units in this case, times the mass of the cold. That's what we're looking for. We're looking for the mass of the cold. We don't know how much water that is, times the change in temperature. So that's going to be 23.5 minus 18.2 degrees Celsius. And so we have to solve for mass of the cold. Let's see here. So what do we got here? All right, so this is going to be equal to, this is a minus 24.4 grams times a minus 11.5 degrees Celsius is equal to mass of the cold times the difference between that is 5.3 degrees Celsius. We divide both sides by 5.3 degrees Celsius. All right. These two become positive, and what we end up getting by doing this arithmetic is we get 52.94 grams is equal to the mass of the cold water, or we can say that the volume of the cold water is equal to 52.94 milliliters, simply because the density of water is 1 gram per milliliter. 1. All right, for this problem, what we've got is we're dealing with Hess's law. All right, and what we want to do is we want to arrange the equations in blue to generate or create the equation in pink. By doing that, once we get that done, we'll then add up our delta H's. All right, we'll add up our delta H's, and that will tell us the enthalpy of this reaction. So the question for this says, calculate delta H for the reaction above. So we need to calculate delta H for this because we do not know what it is. But we're going to calculate delta H from the blue equations, all right, from the blue equation. So I'm going to do this in yellow, all right, and so what I'm going to do is I see that the calcium is on the reactant side, and on this one I have a calcium on the reactant side as well. So I'm just going to rewrite the blue equation. just going to rewrite the calcium equation. Now, I need to come up with the calcium carbonate on a product side. Well, if I look at the second blue equation, I have the calcium carbonate, but it's on the reactant side. So I'm going to write the blue equation backwards. All right? So I'm going to write that one backwards. So this becomes CO2 gas plus calcium oxide solid yields calcium carbonate solid. Now, if this delta H is going to be positive, if I write it backwards, the delta H is going to be negative. All right. If I add these up, take blue, I can see now that the calcium oxide is going to cancel on both sides. And if I write now what I've got, so now I have a calcium solid plus 1/2 O2 gas plus CO2 gas goes to now calcium carbonate. I have the exact equation down here as I do up there. And all I have to do now is add up those two values. And when I add up those two values, my delta H is going to be equal to minus 813.4 kilojoules. In some instances, you may end up having to multiply this by a number. You may have to multiply it by a half, whatever. If you happen to multiply this by a number, you also have to multiply the delta H by that exact same number. If you have to multiply it by 1/2, you have to multiply delta H by 1/2. Okay? If you have any questions on these, feel free and let me know. It says acetylene burns in air by the following equation. So this is going to be the equation, what I have in pink. We have acetylene reacting with 5/2 mole of oxygen to produce 1 mole of water and 2 moles of CO2. And it's an exothermic process, and so it's going to give off 1,255.8 kilojoules of energy. From the heat of formation of these substances, we are to find the heat of formation for the acetylene, which is C2H2. All right? We're going to work off the premise or the equation that it's going to be it's going to be products minus reactants is equal to our change in delta H. So if we look at our products, we have 1 mole of water times the heat of formation of water. Now you have to be careful. This says gaseous water. This is gaseous water. You got to be careful. You can get these heat of formations in the back of the book, but you have to really pay attention to the phases. So this becomes minus 241.8 kilojoules per mole plus, because it's still a product, it's going to be 2 moles of CO2 times a minus 393.5 kilojoules per mole minus 1 mole of acetylene, which is X. Now, what do we do about the oxygen? Well, since the oxygen is elemental, the heat of formation of all elements is going to be 0. It's going to be 0. So we can write minus 0 there, all right, because all elements is going to be 0. And this happens to be equal to a minus 1,255.8 kilojoules. Now, before I go any further here, we can look at this right here. Those are the products. These are the reactants, and that's our delta H. So if we go through and do this arithmetic, or if we go through and we can do some canceling here, we see that a mole cancels with a mole cancels with a mole. Leave that alone because there's going to be a mole unit there. And we go through and we can kind of simplify this. So we get a minus 241.8 kilojoules minus, if we take 2 times the negative 397, we get 787 kilojoules. Yep, that's right. Yes, yep. Minus X is equal to 1255.8 kilojoules. Oops, a negative. Don't forget I should not drop that negative. Now what we do is we can combine terms, right? We can take all the numbers over to here, right? Take these, swing them over here, and we end up getting a minus X is equal to a minus 227 kilojoules. We can make these all positive such that the X, the heat of formation for our acetylene, is 227 kilojoules per mole. All right? Thus concludes the problems for the thermochemistry chapter. If you have any questions for me, feel free to let me know. All right?